This is going to be a video demonstrating phase lock loop with the 74HCT4046 chip, which has three voltage comparators, or three phase comparators, and a voltage controlled oscillator. So to demonstrate what a phase comparator does, this is the symbol for a phase comparator. So if we got two different square wave pulses at the same frequency going into it, but one of the square wave pulses is out of phase by 25%, you can see that they kind of overlap here, and there's a phase difference. Like right here's a difference, here's a difference, here's a difference. So at the point where these phases are different, the phase comparator is going to output high. And when the phases are exactly the same, it's going to output low. So if we look at the output of the phase comparator, it's showing up orange here, going high at the points where these two pulses are different. It goes high. So you can see it's putting out a square wave pulse with the duty cycle that's equal to the difference of the two phases. So to make that square wave duty cycle useful, we go out through a low pass filter, which will average out the pulse and convert it into just a voltage reading, whereas the more out of phase these two are, the higher the voltage. The closer together the two phases are, the lower the voltage output. So let's get rid of some of this stuff and show you just the output from after the low pass filter. Now this looks like triangle wave, but in all reality, it's just a 0.2 volt jump. It's actually pretty stable in between 0.2 volts. So that's a voltage representation of the difference of these two phases. And what can you do with that? Well, you could read that with a microcontroller's ADC, or you can make a phase lock loop. Now, what is a phase lock? How does a phase lock loop work? Well, with a phase lock loop, you only have one frequency being inputted, and you have the output of this frequency. Let me show you here. So you have the output of the frequency from the low pass filter going to a voltage controlled oscillator. So the more different, if you only have one frequency going in, the more different, the higher the frequency the VCO is going to put out. And you put that into the phase comparator, and that creates a feedback loop that makes this system working together self-replicate the frequency coming in. So it's going to create the same frequency as you put in on the one side. Now what's useful about that is that you've replicated this frequency, and it puts out a square wave duty cycle to do that, and then it puts out a voltage to do that, to run the VCO to make it catch up to the frequency. So the output right here is going to be a demodulated FM signal. It's going to be like, okay, if you put in an FM signal into here, this would be the demodulated sound of the FM signal. And this will just keep running the feedback, and that'll give you the output of the sound from the radio station or whatever if you tap in right here. So now on my setup that I'm going to show you, I've got a signal generator putting out a 10 kilohertz sine wave, and then I've got that going into a LM339N, which is a voltage comparator, and all that's doing is turning the sine wave, the 10 kilohertz sine wave, into a 10 kilohertz square wave positive pulse. So it's not going to be low negative. It's just going to be the positive half turned to a square wave. And then I've got the leads for my oscilloscope are connected here for the input square wave, the square wave that's being input. I got one lead hooked here, and then I got another lead hooked here to show what the VCO has created to catch up. So right now I got, those are the two places that I have the oscilloscope leads. So let's check it out on this breadboard. So okay, I know you can't see that LCD screen, but it's a 10 kilohertz sine wave this is putting out. And the 10 kilohertz sine wave is going to this voltage comparator chip, which is just turning it into the square wave. And then the square wave is going into one side, this purple wire, it's going into one side of the comparator. And then the VCO, this is the input of the VCO, this yellow wire, and it's coming off of this low pass filter, the resistor and capacitor, same as this, exactly the same, this low pass filter. So it's coming off the low pass filter into the input of the VCO, and the VCO is right here. So we've got this oscilloscope lead is running to the output of the VCO, and this oscilloscope lead is going to the output of the voltage comparator. So that's the square wave that's going into the phase comparator, and this is the square wave coming out of the VCO as hooked up just like this. So there's one and there's the other. So there's a circuit all running, and here's the output. So notice that they are the exact same frequency at 10 kilohertz. Now if I was to change the frequency on the signal generator, it would because it's in a phase lock loop, it would match that frequency. So let me twist on this knob here and change the frequency. I'm not sure which frequency is which. Let me see. Okay, yellow is the input from the signal generator. So that's on channel 2. So let's turn channel 2 off. Okay, so the bottom one, the bottom square wave is the input from the signal generator. The top square wave is the output of the VCO. And if I change the frequency, oh, that's too far, they will perfectly match because they are in sync. Oh, I went out of range there a little bit. Yeah. So there's a certain bandwidth that it works at, and I went out of that range. But as you can see, it is locked on. It's working with each other, And the biggest problem I had was getting the VCO to work correctly, because you have to use this capacitor and this resistor to set the frequency range that the VCO is going to work in. And that was the hardest part to figure out. I had to try all kinds of combinations to get it within a certain range. And that's why you've seen it, the oscilloscope mess up, because this one is set up between the 2 kilohertz and 25-ish kilohertz range. So anything beyond that, it's going to lose its phase lock. And let's leave this. So here's the chip. These between this pin and this pin's got to be the capacitor to set the output of the phase comparator, and then R1 is the resistor. Well, this is for a frequency, or a frequency synthesizer, but this is kind of similar to what we've got with the phase lock loop. But yeah, the data sheet didn't really help me very much on the setting up the VCO. I just had to try and see. I went by this, and this is not that great, and this one is not that great. This is all talking about which capacitor and resistor to use, but I just had to figure it out using the oscilloscope, and it works. We've got the phase lock loop done. So now I can move on to more things with this. And what you can do with this is demodulate FM signal. You can do frequency synthesizer. You can actually modulate FM signals with this chip. You can do a lot of weird things with this chip. It's a pretty interesting chip. But yeah. So for this, I'm using, for this chip and this setup, I'm using a, well, I tested all kinds of combinations. I settled on a 0.22 microfarad capacitor and a 3K resistor, and that got me in the realm of 2 kilohertz to 25 kilohertz, but it kind of went up to 70 kilohertz, but it got jittery and unstable over 25, so that's kind of the range it's working in. But yeah, this is the phase lock loop. Pretty neat. More to come from that later.